Aloha. On behalf of the Helen Keller Foundation, the family of Helen Keller, I welcome you to the Helen Keller Prize for Vision Research. Each and every Helen Keller Prize is so very important, not for only the laureates whose diligent work we will honor, but also because it gives us hope. Hope that one day there shall be no preventable blindness. One group that is so important to us is the Prize Selection Committee. They do a tremendous job in selecting our Helen Keller laureates. I would like to introduce you to the co-chairman of the Helen Keller Prize Selection Committee, Dr. Nick Delamere and Dr. Joe Hollyfield.
Thank you, Keller, and welcome to everybody. It's a great pleasure to see a lot of familiar faces here tonight, and it's something I look forward to year after year, to gather with the prize winners and to gather with our colleagues who've come to celebrate the prize. There is a face missing tonight, and I just wanted to let people know that we're missing our dear colleague Chris Patterson. Chris sadly passed away March the 30th after a long illness. Chris had been one of the co-chairs of the Helen Keller Prize Committee during its formative period. And Chris, together with Tom Zimmerman, who also passed away a number of years ago, were instrumental in making the prize what it is today. They carried it through some lean years, and they were creative and visionary in what they did for the prize. Chris was a dear friend to many of us in the room, and I can see people nodding their heads in agreement. We miss him dearly, and it's with great respect that I honor him tonight. Thank you.
I'd like to introduce the other members of the Prize Selection Committee. Bronwyn Bateman, Dean Bach, Emily Chu, Joel Schumann, Lois Smith, Al Summer, and Hugh Taylor. Would you guys stand, please?
Thank you so much, gentlemen. I would like to share with you a story that many of you have heard 2 years ago when we were in Seattle. It goes something like this. Dr. Frank Mayfield was touring the Tewksbury Institute when he accidentally collided with an elderly floor maid. To cover the awkward moment, he helped her up and said, "Who are you? What do you do here?" And she said, "It would be better if I could show you." So with that, he took her hand and she led him under the oldest part of the building. As they got to the dark basement, she pointed to what looked like old rusted cells. And she said, "That's where they used to keep Annie." Dr. Mayfield said, "Who's Annie?" The maid replied, "She was a young girl. She seemed wild, deranged. The doctors and nurses couldn't do anything with her. Every time they would put her in her cell, she would just bite and kick, even though they were trying to just help her by examining her." She said, "One night I saw them do this, and I was so outraged that I thought, I'm going to go home tonight, and I am going to make something delicious for little Annie." That night I went home and made her favorite chocolate chip cookies. I brought them to work the next day. I carefully placed them in front of the cage where Annie was sitting. And I said, "Here, these are yours. I made them just for you." And with that, I went on doing my day's work. That's how Annie and I became close friends. Anytime she needed something or wanted something, she would confide in me. And so The doctors and nurses saw this, and they realized that if I would go in the cell and comfort Annie, then they would have a much easier time examining her. After a thorough examination one day, they found out that Annie was going blind. I didn't know what in the world I could do to help her, but I knew someone that could. I made sure that Annie got the help she needed by writing a note to the head of the Tewksbury Institute. Years later, I was reading about a lady named Helen Keller who had just been interviewed for the Nobel Peace Prize that she was up to possibly receive. And during that interview, the reporter asked her, "Mrs. Keller, who had the greatest influence on your life?" And of course, she spelled back using the manual alphabet in her hoarse, wispy voice. "Oh, that's easy. My teacher, Annie Sullivan." Annie Sullivan shook her head, and she spelled into Helen's hand, again using the manual alphabet. And she said, "No, Helen. The lady that had the greatest influence on both of our lives was a floor maid at the Tewksbury Institute." You see, history is changed when one person says, "I will." And if I've learned anything from my Aunt Helen's legacy, I've learned to stand up and to say, "I will." Our next guest, it's her first debut. She's 10 years old, and she is my daughter, also named after her great-grand aunt, Helen Keller. At this time, would you welcome someone who inspires me each and every day, Keller Cooper Thompson.
Good evening. Obviously, I've never had the privilege of meeting my great-grand-aunt, Helen Keller. I'm 10 years old, and she died in 1968. But the many lessons that her life has taught me are ones that I shall carry with me, especially those of courage, faith, and strength. Above all, however, Aunt Helen has taught me that hope is the strength by which a shattered world shall emerge into the light. Thank you all for sharing in that hope by dedicating your lives to help others, just as my Aunt Helen did.
Our miracle worker this evening is a wonderful partner of the Helen Keller Foundation. And it is my privilege to introduce to you the Chief Executive Officer of the Bright Focus Foundation, Stacy Pagos Holler. Stacy.
Thank you for that beautiful introduction on behalf of Bright Focus. And to all of you, thanks Keller, Laura for organizing an amazing evening, the awards committee, and all of the vision researchers who come out every day to save our site and to figure out how we end diseases that will allow us to age the way we'd like. Bright Focus is very, very proud of the partnership with the Helen Keller Foundation, and I don't think you have to worry. Cooper's got it down in there. Along with Helen Keller, there's another woman of great leadership in the history of our country who had perhaps one of the greatest, shortest lines about Helen Keller. Eleanor Roosevelt once said, "Whatever Helen Keller is for, I'm for." And I think that spirit was just shown to us with her legacy. Brief background, Bright Focus funds research worldwide to end diseases of mind and sight. We have 3 programs. The vision programs you all know, I think, fairly well. Macular degeneration, glaucoma, and Alzheimer's. We're proud that we have about 200 projects going on right now worldwide with a portfolio of about 40 million in research sponsorship. We've been in 22 countries, and we'll continue to do everything we can to support your community to end end these diseases and rid us of preventable blindness. The prize recognizes our shared mission about scientific excellence, and it's important. And I would like to just extend to all the previous laureates our special congratulations, and in particular to the laureates who are here tonight: Ted Dryje, Brenda Gailey, Lynn Murphy, Webb Kavanagh. Thank you for being here. So I'd like to close by saying thank you all for being here, but also in honor of Bob Morris, who usually stands up here with us on the award and has this very special quote that I think is even more apropos tonight than in other years. And her quote is, "Alone we can do so little, together we can do so much." Thank you all for what you do and for giving us a moment to shine the light on the researchers tonight. Thank you.
Thank you so much, Stacy, and the Bright Focus Foundation. I would now like to introduce a longstanding member of the Helen Keller Prize Selection Committee, Dr. Bronwyn Bateman.
Thank you very much. By the 1970s, oncogenes had been identified as genes that cause or predispose to human cancer by being activated or inappropriately turned on. In the early to mid-1980s, teams led by ophthalmologist Ted Dryje, Brenda Gailey, and Lynn Murphy, basic scientists, primarily Webb Kavanagh, successfully mapped and cloned the gene responsible for the childhood eye cancer retinoblastoma. Not only was this RB1 gene primarily responsible for retinoblastoma, but it also turned out to be the prototype of a new class of human cancer genes, referred to as suppressor cancer genes or anti-oncogenes. Today, more than 30 years later, it is known that most cancers, with the notable exception of the leukemias and lymphomas, carry mutations in anti-oncogenes. Genes in this class act normally to prevent cancer. They cause or predispose to cancer by having their normal function of controlling cell growth impaired or knocked out by a mutation or a chromosomal deletion. It is the scientists that collectively identified and defined the first human cancer suppressor gene, RB1, that we honor today. This body of work has had a domino effect in cancer medicine and has made the world a better place. Thank you to the researchers.
And now for the 2018 Helen Keller laureates. First, I must tell you that each laureate will receive an honorarium, a framed citation, and the Helen Keller medallion. As I'll call and introduce each one of you, if you will come to the stage. Dr. Webster Kavanagh. Dr. Ted Dryje. Dr. Brenda Gailey. Dr. Lynn Murphy cannot be with us this evening, but standing in his place is Miss Jessie Berry. Congratulations to our 2018 Helen Keller laureates.
So, as we go through this story, you will see, I can't indicate, but you'll see there are bubbles on the slide for Webb, Ted, Brenda, and then me as Lynn. And we will talk a little bit about the contributions that were made by these 4 really wonderful and impactful individuals in terms of the RB1, the first ever described tumor suppressor gene.
Sure. So we're going to go through the history of the gene and how the knowledge we have today all came about. We have to start with Al Knutson, who was a pediatrician who looked at the simple clinical data of age at diagnosis of children with retinoblastoma. And he recognized that those that had tumors in both eyes, bilateral retinoblastoma, were younger. And you can see on the curves here where he plotted mathematically, because he loved mathematics, he took common data that had been known for 100 years and no one had paid much attention to, and he made it a key underlying principle of cancer, as Dr. Bateman just described. So on the vertical axis is the fraction of children not yet diagnosed at the age indicated on the x-axis. And so at 0, 100% are not yet diagnosed. And retinoblastoma is not like most cancers where you get more and more cancer as you get older. It happens very early for very important reasons. And the ones that are shown where I've got 2 hits are the unilaterals. They had to have 2 different events to get the cancer to start in their one eye, and they only got 1 tumor. Those that had bilateral retinoblastoma were predisposed to get retinoblastoma in both eyes, and all they needed in each tumor that developed was 1 more hit. And that's the key principle that started retinoblastoma being such an important cancer for all cancers. So then we know there's 2 kinds of each chromosome in every cell, so that counts 1, 2. So we're going to do a lot of counting 0, 1, and 2 in this talk. And Eunice, and then my group, led by first author Louise Knight, did really simple work looking under a microscope at chromosomes. And what the figure shows here is a pedigree, and you can see that the mother, who I've indicated maternal chromosome 1 and 2, she had unilateral retinoblastoma. Her eye was removed, and she carried on with no knowledge that retinoblastoma could be hereditary at all. Her second child was diagnosed with bilateral retinoblastoma at about 18 months of age. 1 eye was removed immediately. The other eye was treated with intraarterial triethylene melamine, a very toxic drug, and radiation. And then the eye was later removed because the treatment didn't work, and then the child died of metastatic disease. The third child was diagnosed at 10 months of age with bilateral retinoblastoma, but 1 eye was removed and the other eye was saved, and the child carried on through life. So looking at mapping, where could this linkage thing be? That was the marker that Louise Knight could see was detectable under a microscope looking at the chromosomes. So you could tell which chromosome carried the retinoblastoma predisposition. You can see it's maternal too.
And further linkage studies done early on in Dr. Murphy's career showed that a decrease in the enzymatic activity for esterase D were also linked to the same physical location on chromosome 13q. So this was all of the initial physical and genetic evidence looking at 13q as the location for this first described tumor suppressor gene.
So Ted and I and others collaborated to look at the isoenzymes of esterase D. So I'm showing you here a starch gel electrophoresis. Many of you don't even know what that could possibly be, but that's what it was. This was 1983. You'll notice that the journals that published this work on the rare cancer retinoblastoma are pretty impressive journals, so somebody recognized it was important.
And I'll particularly focus on the numbers that are written there. Well, first of all, the first 3 lanes have 3 bands. And that's because this is an isoenzyme, and so you have a band for 1,1, 2,2, and 1,2, different abilities to move through the gel, the starch gel. And you can see the retinoblastoma 409 has 0 copies, 0 evidence of protein from esterase D, and the fibroblasts have the normal 3. And I'll point particularly to tumor 412, and you can see that the fibroblasts have 3 bands. The 1 clone A has 0, and 412, a different B, is a different clone, has 1. So there's 2 different tumors in the same eye that are actually mixed together in terms of how much esterase D they had. But the real important message here is that those tumors have lost the functional activity of a gene that is very closely linked to the unknown retinoblastoma gene.
All right, so this is where we came in.
Closer to your mouth.
So this was kind of an interesting story. So maybe I'll digress a little bit because I was not in the ophthalmology community, still am not. In fact, I was a Chinese hamster cell geneticist. And I hooked up with another guy who was a Drosophila geneticist. So you might say, what does any of that have to do with retinoblastoma? And the answer is it has almost nothing to do with it, except that we were interested in genetic transmission. So we had gotten a large grant from the Howard Hughes Medical Institute to develop a technology and the application of that technology for developing the first human genetic map. So the human genetic map was limited by several things. One was families that had structures that were understood. And the second was that really the only markers we had were the markers like Brenda just showed you, which esterase D, there were a variety of these, but maybe only 40 or 50 in the human genome, so not very close together. And those markers usually had a pretty low minor allele frequency, which meant their mapping information was limited, which meant that even if you collected families, you didn't get much information from them. So we decided that what we were going to use was a way that we could look at DNA sequence variation, and that sequence variation would be the genetic marker. That is, we would look for DNA sequence variation that happened between one person or another and use that to follow the transmission of chromosomes to which those markers mapped in families. Along the way, of course, we developed the technology. It was very laborious. I have to say very laborious. And took several years actually to get moving. But once it got moving, it moved very quickly. And then the question became, what's the problem? So we have a technology, but what's the problem? And then we came across Brenda's esterase D paper linking a cancer that we had never heard of. Hamsters actually don't get retinoblastoma, and neither do Drosophilas. So for us, this was a cancer's a cancer. What the heck? We have a problem. So we started to focus on developing sequence markers along the length of chromosome 13 because that was where esterase D mapped and where esterase D had been linked to retinoblastoma. So we developed a bunch of markers. That was 2 years worth of work, what I just said. And those markers showed these polymorphisms between people and between, in fact, between chromosomes in people. And so we realized that these markers would be something that we could do a fancier version of what Brenda just showed you with esterase D by using these markers to follow chromosomes from constitutional tissue, in this case it was fibroblasts, into retinoblastomas. So you can see this RB412, you've already heard that from Brenda. So this is one of her patients in which she had isolated the fibroblasts and the tumor cells, and we looked to see what happened. And what happened was that cells which were heterozygous, that is, had 2 different kinds of chromosomes, became homozygous. That is, they had only one kind of chromosome, and that kind of chromosome, we inferred, must be the one that carries the mutation. Now, I say the word inferred because, of course, we didn't know that. We just thought it might be so, and we sold it to nature, but we really didn't know. And we really didn't know until we did this experiment, which is shown here. And what we did was to take families that had retinoblastoma, like the one that Brenda showed you, and follow those families through generations in which we could follow the chromosomes. And of course, we had two different ways that we could understand which set of chromosomes these people had. We could either look in one parent who was affected and then a child who was affected, and they should share the same chromosome, and in fact they did. Or we could look in the tumors of one of these patients and show that they had become homozygous, and therefore that chromosome should be the one that had the mutation, and we could follow that through families too. So it was interesting, actually. Nature turned that paper down. And I talked to Peter Newmark at a meeting. Peter Newmark was the editor of Nature, and he said, and I had presented this, and he said, well, why didn't you send it to us? I said, we sent it to you, but you didn't want it, so we sent it to Science. They took it on without any comment. I said, I guess the lesson is clear. So then we realized that by what I just said, by being able to follow these chromosomes in families, either from tumors into people, into progeny, or from parent to progeny, that we should have a way that we could tell whether a young child, just born, for example, or even amniocytes, which we didn't do, but which we could do, we should be able to tell whether they had the chromosome which came from the affected parent, in familial cases, which had the constellation of markers which predicted for the development of disease. And Brenda's going to show you a case at the very end which shows you that this is a very useful thing, actually, clinically to be able to do. So we showed that that could be done, and we sent that not to Nature, but to New England Journal of Medicine, because we wanted to be able to put all the caveats that were there, because there were several caveats, and Ted will talk about those at the end. So one caveat is that there's recombination between chromosomes. So if the recombination happens and moves the RB gene around, we wouldn't know it because we're looking outside of those recombinations. The probability of that is that multiplicative probability, which means that this test was probably 80% or so accurate. The first premorbid detection of a cancer, by the way, but still only about 80% active. What we really needed was to be able to follow the precise mutation. The other thing that I think was said was that these patients, Brenda said, these patients who are bilateral retinoblastomas are also predisposed at a pretty high frequency to second site primary second site tumors, which are non-ocular. And the most common of those is osteogenic sarcoma. So these patients, even after they're treated for bilateral retinoblastoma, when they're teenagers, develop osteogenic sarcomas in the bone plates. And so we wondered whether this was because the mutation that they inherited was actually predisposing not just to retinoblastoma, but also to osteogenic sarcoma. That is, was it pleiotropic? Because if it was pleiotropic, then understanding one of these genes could actually explain several kinds of cancers. And so Ted and I collaborated, and Brenda and I collaborated on a couple of papers here, one of which showed that osteogenic sarcoma arising in retinoblastoma patients had exactly the same homozygosis in the tumor as did the retinoblastomas. And then with Ted, we showed that in non-retinoblastoma cases of osteogenic sarcoma, they had the identical fingerprint. So this looked like now, this gene was not only responsible for retinoblastoma, but for osteogenic sarcoma, as it turns out for others now too. But that was all driven because of the clinical features of the familial associations that we had learned from all of our friends, about which, of course, we knew nothing. So we were left with what's really the gene, because now we can have precision, and that's
I think I got mine. Yeah, here we go. So this blot is blot number 507, and it was made around September of 1984. I still remember the day that Joyce Rappaport, the second author here, brought it to me while I was meeting with my mentor, Dan Albert, and she had to show me the findings. It's lane number 9 that you're supposed to look at. The lane between 13 and 14 is blank because the DNA got clogged up in that lane. It just didn't work. The 3 lines of bands you see here labeled H242, H38, and 72, those were names for probes looking for different pieces of DNA on chromosome 13, which we thought were near the retinoblastoma gene. And it was sort of an offhand blot 507. We said, we have this collection of DNAs. Each lane is a different retinoblastoma from a different patient. Most of these tumors came from retinoblastomas that I had collected from patients and ophthalmologists through New England and even farther than that. And we had this collection of DNA. Some of them even came from Brenda Galley and Lynn Murphy and so on, but most were from my group. And we had this collection of DNA. We were at a state where we had probes that could look at pieces of DNA or look at chromosome 13. And the chance that one of these probes would actually find a deletion in a retinoblastoma that was homozygous, that is a piece of DNA that was completely missing, was probably pretty low, but we had all the resources and the blot took less than a week to put together. And the surprise was probe H38. You see lane number 9 has H38 completely missing, which means that some retinoblastomas did have homozygous deletions, knocking out both copies of the retinoblastoma gene, and also that H38 was very close to that gene. So then over the next year we started, nowadays, now that we have the whole genome, we realize how lucky we were in one respect, because those 3 probes are now known to be millions of base pairs of DNA straddling around chromosome 13q14. H38 was right in the retinoblastoma gene by chance. Esterase D was over 1 million base pairs away. The other probes you can see were millions of base pairs away. We didn't know how far all these things were, and we knew H38 was in an interesting region. So we started to do what we call chromosome walking. And remember, I just showed you the chromosome that was measured in millions of base pairs. And here we're walking a walk that took over a year, maybe longer, and we only went thousands of base pairs. So we were not walking, we were crawling. And during this walk, a comparable walk was going on across town with Lou Conkle, who was trying to find the Duchenne muscular dystrophy gene. It was also being organized because of a deletion of chromosome X that Lou Conkle had. And as he was walking along in his deleted area and we were walking around in our deleted area, we occasionally would talk to each other about our progress. And he told me that in order to find a piece of DNA that he thought might be a gene, he noticed that one of his pieces cross-hybridized. It seemed to have sequence homology with not only human DNA, but also with rodent DNA. And that struck a little light in my mind because one of the pieces of DNA that we had been walking along and finding had that same property. That piece of DNA, probe P7H3O.7R, we then used to see if it encoded a gene, and that was done in collaboration with Stephen Friend, who was working at Bob Weinberg's lab at across the river. And indeed, it did show a transcript, 4.7 kilobases as seen here, present in the retina and not present in 5 retinoblastomas that he showed. And with that probe, we were then able to map out the entire gene and show by various mechanisms that that transcript actually came from the retinoblastoma gene. That mapping, I don't know, together, it was both my group, together with Janie Wiggs, did a lot of that work actually mapping out who's here in the audience now. And then independently, Murphy's group and other groups were able to map out the entire sequence, or entire restriction map or sort of rudimentary structure of the gene over the next couple of years. And it's with that structure then that the clinical advances came. And now Brenda? Okay.
So these researchers were These researchers were also able to describe saliently that the MYC-N, which is an oncogene, so as was discussed previously, a tumor activating gene instead of a tumor suppressor gene, was able to drive retinoblastoma. So Dr. Murphy was one of the first researchers to discuss the expression and the amplification of the NMYC gene in primary retinoblastoma. And then Galley went on to show that the tumor induction by the retinoblastoma, the RB1 tumor suppressor gene, is independent of NMYC expression. However, very recently, there's been even more salient research regarding NMYC.
So we were very wise. We said, oh, MYC-N is expressed in retinoblastoma just because it's a neural embryonic tumor. And we left it like that until we were busy looking for 2 retinoblastoma mutations in tumors and realized that we had some tumors, very rare, 2% of unilateral, we could not find any mistake in the retinoblastoma gene. And then we realized that those tumors had very high level copy number of MYC-N. So they had really amplified, more than 10 copies, between 10 and 128 copies of the MYC-N oncogene, and no damage to retinoblastoma. So this is a figure from that paper comparing to Knudsen, and you can see the yellow arrow showing 2 RB hits. That's 2 copies of the retinoblastoma gene mutated, and that's the same mathematical look at age at diagnosis that Knudsen had done. And you can see that all the dots fit the blue curve, which is a 2-hit curve. And we're looking for that exponential curve, and we find that, in fact, it looks like the early dots, there aren't so many because we didn't have very many of these MYC-N tumors, and we had to collaborate with 5 centers worldwide to get enough data on these rare tumors. But we think that those show that the oncogene, when it's highly amplified, drives the tumor without any other mutation. They don't need to have any predisposition. They're all unilateral. I must say, though, that the first patient that was recognized to have a tumor with MYC-N amplification and normal RB1, the eye was removed by Emily Chu when she was covering for me at the Hospital for Sick Children when I was on a year of sabbatical doing this work on MYC-N. So that was for the second paper there, when Emily gave me a year's sabbatical. That patient, we later realized, was the first one we really knew had a MYC-N amplified driven tumor, and that patient is now a pediatrician. He was on the news when this paper came out. He knows all about his tumor and its implication, and he has 2 normal children because this is not going to be able to be heritable.
So retinoblastoma, aside from being one of the first human cancers to have a described and delineated tumor suppressor gene, was also one of the first cancers to have genetics in its staging for prognosis. And much of this stemmed from early work in 2005 by Dr. Murphy. So prior to his work in the 1960s, is that right? There was the Reese-Ellsworth classification, which predicted tumor response to treatment. So very important when you stage a child, right? We do this work because we're clinicians and we take care of patients. To stage a child in their response to treatment and to radiotherapy, which was the primary treatment at that time. And then as our treatment methods changed and we moved into an era of chemotherapy, it was needed to have a different staging classification, which was described in collaboration, but with a lot of effort from Dr. Murphy. And this new group classification was used for children's oncology trials and for trials, really trials and treatment of children all around the world until very recently when retinoblastoma moved to the AJCC-TNM staging, which has a very special impact as well for retinoblastoma.
So just on the new AJC retinoblastoma cancer staging, which is intended to predict prognosis, for retinoblastoma, the prognosis that you might be able to save a particular eye, and most importantly for cancer, to save lives. So the that data that forms the 8th edition for the clinical outcomes is the product of a global collaboration, and some of the people who contributed a lot of patients into that collaboration. There were 3,000 patients altogether, and their details of presentation and then their outcomes are all contributed to the new staging. But Ashwin Malapatna, who's now in Australia, was the key person to push forward uniquely to establish that genetics has a key role in outcome for cancer. And we all know many, many cancers, as Bronwyn said right at the beginning, are in fact genetic diseases. But the only cancer that can claim heritability as a key factor is retinoblastoma. So HX means we don't know. That would be a unilateral and we don't know anything about, no testing. H0 would be for a offspring of a patient who had retinoblastoma, and that child, and you know the parent's mutation and the child doesn't have it, that's H0. And H1 is bilateral retinoblastoma, trilateral, or a close family history, or the molecular definition of the mistake in the retinoblastoma gene. That's H1. These terms are very useful, and obviously we know that genetics has a lot to do with outcomes.
And while it is beyond the discussion tonight, and we know you're all waiting for dinner as well, it should be noted that much of this work and the identification and the delineation of this RB1 tumor gene is critically impactful for children. So in most centers in the US and around the world, when children are diagnosed with retinoblastoma, they have serum testing of their RB1 gene to see whether or not they have the heritable form of retinoblastoma, which is not just bilateral, it can also occur in unilateral cases, or whether they do not, which predicts the risk of developing other tumors in the eye, other tumors outside of the eye, as well as giving that gene to their children.
So I'm going to tell you about one more family. You can see that the mother, who's now you know what H1 means, she had her both eyes removed in the 1950s, which allowed her to have a family and a life until she died of her sarcoma, her second cancer. Her first child also had retinoblastoma, but because we knew the mutation, that child has 2 eyes with 20/20 vision, and I treated her in the 1990s. Her brother didn't carry the mutation, so he didn't get retinoblastoma. The offspring of the mother in this diagram, the first child was H0, and the second child tested by amniocentesis at 32 weeks gestation was found to have the mutation. So we knew that baby had a high risk of having tumors early. So she was delivered at 36 weeks gestation, which is our standard care for patients who we know are going to get retinoblastoma, like this child. And then we follow them by looking at the baby's eyes with the RetCam and OCT, handheld bioptogen OCT. So the pictures aren't so pretty as the fancy big OCTs, but they show a lot. And you can see in the first row, those little black arrows are pointing to where the tumor is, very much on the edge of the fovea. And then you can see on the OCT on the right that that's approximately a 40 micron retinoblastoma in the internuclear layer of this child's eye. But it's invisible. So when you laser this tumor, you have to first put in a burn and see if you're in the right spot. So you have to follow the blood vessels and map it out. It's very difficult. And you can see that in the left picture on the second row, that there's a little white burn, and you can see by the OCT it hit the tumor perfectly. That was one laser burn. And then 8 more laser burns were put into that tumor, and that's all we did. And the picture at the bottom across shows the strange-looking scar right on the edge of the macula, but the OCT shows, this is 6 months later, that there's a scar, the pigment epithelium's lost, and the retina sort of tucks down there because of that, but the axon layer is crossing that scar intact. So that's how minimal the therapy could be to destroy this tumor. The child now has 5 other tumors, and all of those are treated with laser, and there's going to be no visual loss. She shows that all this work for the retinoblastoma gene can really change vision and life. And we thank the Helen Keller Foundation very much. Yes. But we would like to thank all of you for recognizing retinoblastoma with the Helen Keller Award, and we thank the patients who've contributed to all of our work and our families and all that stuff, but mostly we now can look forward to a world of no blindness from retinoblastoma and move to the next goal of no deaths from retinoblastoma.
Thank you so much. What wonderful work. Again, your 2018 Helen Keller Laureates.